In this video, I'm going to teach motion diagrams to analyze events. A motion diagram is a tool to help develop an intuition about motion and the relationships between position, displacement, velocity, and acceleration. Let's start with an event of which I took a video. Okay, we saw a tennis ball roll down an inclined table. Now that object had a position, velocity, and acceleration function, but that's not what motion diagrams are about. In motion diagrams, we take snapshots of the motion. So to do that, I grabbed one frame of the movie, the frame immediately after I lifted my finger from the ball and it could start rolling. Now I want to represent the location of that ball with a point. Next, I grabbed a frame exactly a third of a second later. I'm going to represent its location there with a dot. Then I grabbed a frame exactly a third of a second after that. Repeat with a frame a third of a second later. And frame 8. Now on one page, I have 8 different snapshots of where the ball was, represented by points, each exactly a third of a second apart. This is a motion diagram. I've blown it up so we can look at it more closely, and I've labeled my 8 points 0 through 7. What can we do with this motion diagram? The first thing we can do is look at displacements. I've identified by a vector the displacement between each point in time, and I've labeled them delta r sub 0, delta r sub 1, etc. Remember where displacements come from. If you assume some coordinate system, I can establish a position vector, r sub 3, that tells me where that point is at the dot labeled 3, and I have a position vector, r sub 4, for the dot labeled 4. The displacement then is the difference between those two position vectors, r sub 4 minus r sub 3. To see that, you can rewrite that in terms of r sub 4 is equal to r sub 3 plus delta r sub 3, and you can look at adding the vectors with the tail-to-tip method. The tail of delta r sub 3 at the tip of r sub 3, and then the resulting vector r sub 4 goes from the tail of 3 to the tip, and that does not depend on the location of the coordinate system. If I have a different coordinate system, I'll have different position vectors, but the displacement vector is the same. Back to analyzing the displacement vectors, what can we say? Well, they're all pointing in the same direction, which we know. The magnitude is getting larger as time goes on. In fact, just for fun, we can do some numbers. I took a measurement of some lengths of the table as seen in the video, and then compared that to the picture on my screen, and I was able to come up with a conversion of about 12 screen pixels per centimeter in the video. Given that, I can come up with a tabular description of the motion shown here. The first one, between 0 and 1, 1.83 centimeters, all the way to the final one, which was 20.7 centimeters. With those numbers, we can calculate average velocities. Remember, the average velocity is equal to the displacement divided by the time interval, and the time interval is the same in each case. So I can find the average velocity between point 0 and point 1, which is 5.5 centimeters per second. The average velocity between point 1 and 2, and so on, until we finally get to 63.7 as the average velocity between point 6 and 7. I've shown the magnitudes in the table. Of course, the average velocity is a vector, but the average velocity is always pointing in the same direction as the displacement vector. So we could put the average velocity vectors on the motion diagram as well. That's what I've done here. Now remember, before with the displacement vectors, I was able to make a correlation between pixels and centimeters because it was all a distance. That's not the case here. These velocities have units of meters per second, so the actual distance that they cover on the screen doesn't have a specific meaning. It's not in units of length. However, the relative size of the vectors on the screen do correspond to the relative sizes of the average velocities. Now we can go ahead and start calculating the velocity differences between the average velocities. And I've done that graphically simply by copying and pasting these first two vectors, and then just flipping v sub naught 180 degrees, and then adding the orange vector from the tail of the first vector to the tip of the second. So this is the difference vector between the average velocity v sub 1 minus the average velocity v sub 0. I did that again here, calculating the next difference between the average velocity v sub 2 and the average velocity v sub 1. Same method, I just copied and pasted the vectors. I flipped v sub 1 round 180 degrees, then put the resulting vector, tail of the first, tip to the second. I offset them here slightly so they're not directly on top of each other, but we've noticed that it's all in one dimension. I did that again for the next two vectors to get the velocity difference between them, and then finally the final three. The velocity difference stays pretty much constant throughout. With velocity differences, we can calculate which is just the velocity difference divided by the time interval. In each case, the time interval is 6 seconds. It takes 6 seconds to cover two subsequent average velocities, 0 to 2, 1 to 3, etc. So these orange vectors represent the relative, and we put them over the point between the two velocities from which the average acceleration is calculated. So now look what our motion diagram is telling us. It's telling us that the average velocity continually increases. Just for fun, I went ahead and did those calculations, and we see that the average acceleration is at about 1.4 centimeters per second. Actually, this is meters per second squared. I've already converted it to meters. And this is consistent with our understanding where when the acceleration and the velocity are in the same direction, the object is speeding up, whereas if they were in the opposite direction, the system would be slowing down. So that is a look on setting up and using motion diagrams to analyze a system in motion.